It is my absolute pleasure to introduce the first speaker of this session, which is Alexis Boukouvalas. He has a background in computational biology at Manchester, followed by a pretty impressive series of AI-related positions, if you read his bio. His current position is Research Engineer Team Lead at Google DeepMind, and he's going to kick us off with what looks like an amazing overview of some very interesting AI applications in science. Thank you very much, Alexis. Do you want to use the clicker?
Yes, thank you very much.
Thank you so much. Welcome, Alexis. Thank you.
I don't know where to look. Okay. Thanks, everybody, and I appreciate the invitation. Cool. Okay. So hopefully you can all hear me. I have way too much stuff here. Oops. Yeah, I have too much stuff in here. So please have a look also. I'll kind of go through quickly a lot of things. I hope you find them interesting. Please come talk to me. I really look forward to discuss in this conference. Right, so what's Google DeepMind's mission? As you can see, it's building AI responsibly to benefit humanity, right? And I'll just give you the first section here. It's just some of the things that have happened in the company, right? A big part of a lot of people in Google DeepMind's focus is on science and the intersection of science and AI. And why is that such an exciting and interesting space is because we see a lot of data becoming increasingly available, and this is across science, right? So you have a picture here of basically the CERN collider there. We have, in biology, it's just unbelievable, an unbelievable explosion of data availability. As Michel just showed, right, in astronomy, right, you have a lot of things. Fusion, it's, more and more experimental results are becoming available, and weather, right? So these are just some examples. And basically how Google DeepMind works is we are a fairly small team, right? To give you an idea, basically the science team in Google DeepMind is about 100 people. So we try to identify root node problems, right? Problems where we think we can have the maximum impact and help the most people to make progress, right? So this is kind of a this side, a very famous strand of work, right? So you care about drug discovery. You really want to, cure disease, right? How do you, like synthetic biology, there's a lot of, advances you could do here. There's a common thread, like protein folding and actually also understanding DNA here, right? So these are basically the problems that are being attacked by the science team to enable everything that kind of stems from it. And what I'll be talking most of the time here is about what I'm particularly excited about. My recent work is on geospatial intelligence, really understanding what's happening on Earth, the planet's surface. And I will actually start by talking about specific why this is useful, right? So solar potential, there's a big drive to change energy generation, so we use solar power. So we can leverage understanding the geospatial context to make a lot of progress here. Just understanding and making sustainability impact, right? So thinking about deforestation, sustainable supply chains, all these things, the root node problem is understanding what's happening on the surface of the Earth. And just as another big thing there is agriculture, right? There's huge applications. All right, so before I go into that, just very briefly what's been happening. This is a little bit delayed. All right. So AlphaFold, I won't talk about AlphaFold, but people, I suspect, already know a lot about it, but it's predicting the 3D structure of proteins, right? So this was a very successful large-scale program that's still going on, and a lot of people are already using the outputs here. But going beyond that and really understanding what's going on at the DNA level, this is another example actually of what I think is a common thread in AI for science, which Michel also highlighted, right? You actually have a lot of data, but typically you don't have a lot of labels, right? And this is very much true in biology, right? So if I make a mutation in a particular piece of DNA, right, is this going to lead to disease or not? Actually, we don't know the effect of most mutations, right? So this is an area where this AI revolution can really help. And there's been some recent work, I'm just highlighting it here, about understanding the effects in kind of proteins. So this is the coding region of DNA, and also non-coding, which is basically regulation. There's a lot of work there, lots of potential applications, drug discovery, etc. There's also a lot of work on fusion and understanding how to control plasma. This is a collaboration with EPFL, and it was a publication also. Please, have a look and talk to me if you're interested. There's also just thinking about mathematics and doing automatic proofs. For example, understanding, taking part of competition. There's a lot of work in this area, so please, have a look. And also things, I already mentioned weather. So currently the state-of-the-art weather prediction model is a pure machine learning model, which is called GraphCast. GNOME there, which the logo seems a bit messed up, is basically designing new materials, right? So there's also been a lot of progress there. Alpha geometry, talking about solving geometry problems, so people are attacking this. And fan search. So fan search is very interesting also because it's a way of using essentially deep reinforcement learning to design new algorithms. And this has proven successful, for example, right, to design new sorting algorithms or new matrix multiplication algorithms that are faster than anything any human has designed. So this is very exciting. And one thing also, because Michel already mentioned LLMs, so I would be remiss not to talk about LLMs also. And I was thinking specifically for science, right? There is a lot of laborious, grunt work that happens because data very oftentimes is very messy. So and I spend a lot of time, right, just putting things together, sorting out metadata, all that stuff. I'm just highlighting for all of you out there that big LLMs like ChatGPT or Gemini, right, are already very good at helping in this area. So think about having an assistant next to you that is your automatic data scientist that helps you understand data, do quality control, put things in the same format, etc. And also to mine the scientific literature, right? So this is the example here, right? I'm looking at a particular gene here. Please tell me all the research papers that say anything about this gene or related genes, this kind of work. So this already works. All right. So after this kind of whistle tour, I want to talk about geospatial intelligence because that's what I work on actually, and also what I think would be the most also interest in this setting. Right? And I'll start with 2 case studies. The first one about solar potential. Right? So there is actually already in Google available. It's a service which assesses solar potential. And the whole idea is you have a house and you want to put solar panels on it, right? But you want to say, when will I benefit from this, right? I will pay X for this. Now, tell me, based on the orientation of my roof and where my house is and all the kind of historical kind of weather, how much, when will I pay off? When will I start making money, right? So to do this effectively requires remote sensing, right? Requires remote sensing expertise. And specifically what you need to do is you need to build these digital surface maps, right? This is currently done with aerial imagery, so high-resolution aerial imagery. And that map on the top shows you we don't actually have high-resolution aerial imagery for a lot of places. And the current product out there relies on having this. Once you have this high-resolution imagery, the whole ball game basically is to identify the houses, right? Segment the roofs and find the orientation of the roof. So you can say specifically, you can make an accurate calculation of solar potential and how much power you're going to get, right? But there is this problem about availability of high-resolution aerial imagery. You also have low quality, like low resolution, much more widely. You also have remote sensing, like Sentinel-2 optical imagery, right? It's available everywhere. So what people have been doing, teams in Google, basically, right, is you take a lot of different types of imagery, you feed them into basically your large-scale neural network, and you get out basically a segmentation problem, which identifying the houses and the roofs, right? And the orientation here. So this is the surface model. And this goes in and gives you basically your answer. So the whole solar calculation is actually quite involved. It even involves an economics model as well. You push all of these through, and then you get an answer that's hopefully quite useful. This is available. You can actually already use it. It's not available globally, right? And these folks are the people who actually did the work. But the idea is to actually, the next step in this work is to use remote sensing and have global coverage. So anybody anywhere on Earth could do this, right? And this has high sustainability impact. But this is like one specific example, right? I want to talk about another case study here, right? Which is dynamic world. This is also out there. You can use it. This is a global land cover map, right? So this is quite a large model, right? It's been trained using more than 24,000 Sentinel-2 images. It's high resolution, so you have 10-meter resolution, right? It's constantly being updated as new acquisitions, new imagery is obtained, right? It's free, open source, etc., right? And it's basically available in Earth Engine, so you can easily use it, right? And the idea is you can help decision makers, right? Like state government, national governments, NGOs, conservation NGOs, etc., to figure out what's going on, right, in their area of interest and track change in time. Now, what is this model, right? This is a like classical supervised AI model, and these are the classes, right? So it's identifying where there is water, where there is flooded vegetation, where there is a built-up area, where crops, where we have trees, grass, shrub, snow and ice, right? And that's it. This is a fixed set of categories, right? And then you crack the handle and you make this work. And then you can basically use this to do classification of near real-time images, right? You can also, the model quantifies its uncertainty. So quite often you will see for this particular case, sometimes it really gets confused, for example, between grass and shrub because they look quite similar. So, but you know, you can look at the probabilities, and then based on these, you can build derivative map products, right? So specifically things that you're particularly interested in. For example, if you're monitoring deforestation, you really care about forests, right? So forest versus non-forest. Now, how does this actually work, right? And this is a significant effort that you know, a team in Google worked on for you know, more than a year, where you basically collect a lot of data, right? You build a significantly large model. You collect annotations, so actually hire people to annotate where it's water, where it's crops, where it's et cetera, right? So this is what's happening here. And it's a very big exercise in building up the training data that you require to build such a model, right? And then what you have is, once you are satisfied, you validated the model, you assessed it's good enough, then you can run it all the time on any new image, and it will do this segmentation. Now, this is the training data set. It covers all of the Earth. It doesn't cover, for example, Greenland, because there's mostly ice. Nothing that interesting, but I guess that's changing. This is not such a trivial problem, right? Because when you're looking at optical imagery, the thing you will already notice is you have to worry about clouds, right? You can't see through clouds in the optical spectrum, right? So, and this is an example of a problem that anybody dealing with optical remote sensing data has again and again and again, and people are solving it again and again and again. This is an example of wasted effort, right? or even worse, not having basically the best results you could have for your particular application, right? You cannot use this image for training data. It's all cloudy, right? You can actually have another model to identify where the clouds are and just remove them and just mask that out and then use the rest of the image. So people, this is kind of one approach. And once you solved all these problems, basically the whole infrastructure problem and the whole kind of how to deal with clouds, data quality control, you know, Earth is a sphere, so you have to worry about UTM projections, all these complexities. You've done all of this, and now the idea is every time we get a new image from Sentinel-2, you know, we immediately run this algorithm, and basically from this is the start date of when we have data, 2015, for Sentinel-2, and to basically up to like 2 to 5 days ago, you have an updated run of the model, which basically tells you what's going on in this area, right? So this is very exciting, but both of these examples that I showed you are, I guess, fairly large, dedicated teams that solved this particular problem, right? Land use and how it's evolving in time, and like solar potential, right? Can we help anybody who wants to basically have more responsible decision-making and leverage and get insights of this mountain of data that we have from remote sensing, but to do it much more easily? And this is the pitch, this is the idea behind building a foundation model on remote sensing. Now, this is also a brief overview of machine learning for remote sensing data, right? The classical approach, the traditional ML approach, is to basically, what Michel talked about, right? Talk about feature engineering, do a lot of that, you know, like this takes a lot of intuition, a lot of trial and error, right? Because these images are very high dimensional, right? So you really need to do that before you apply your classical machine learning model, something like a random forest, for example, right? Or linear regression. The nice thing is these are very easy, fast to train models, right? You don't need that much data, assuming you do your feature extraction well, right? But this feature engineering is a very laborious, error-prone process, right? So, and such simple models have proven in the past not to be as accurate and as scalable as deep learning approaches. Now, deep learning, right? So this has dramatically improved accuracy for a lot of different problems with remote sensing. I just showed you some examples, right? You don't need to do feature engineering, exactly what Michel said, right? Because that's part of the model, right? But you need a lot of data. You need a lot of labeled data, and you need significant compute. So you need to be well-funded to do this. Right. Can we do better than this deep learning approach? And the answer is to look at a foundational model approach, right? And for foundation models, what is going on? And the whole idea is this self-supervised learning that also Michel described, right? So you just look at the images. You don't look at anything else, right? And then you crack the handle, and I'll explain how this works, right? And then you can basically either fine-tune the model on the set of labels that you have, or actually something called low-shot learning, where you actually don't need any labels at all, right? If this works, and you know, we believe it does, basically you don't need to do feature engineering. It is highly accurate, so it keeps basically the advantages of deep learning. But you no longer need, you know, huge amounts of labeled data. And the really nice thing is this kind of trunk that you build the foundation model, you can use it on many, many tasks, right? So you don't have to keep reinventing the wheel. You basically can start already from a quite advanced point. Okay, so how this works in practice, right? You collect a large unlabeled data set. Now, in Earth Engine, we have more than 25 petabytes of remote sensing data, right? This is all of Sentinel-2, for example. You pre-train this large single model, right? These models have typically billions of parameters, and you'll use the self-supervised technique that I'll talk about. And then you either fine-tune or you do this low-shot training, Okay, I'll keep it short. The analogy to think about is actually large language models, right? So if we think about language for a second and not remote sensing, right? You try to do this next token prediction, right? Large language models operate on the same principle, self-supervised, right? And basically, you mask out a bit of text and you ask the model to try to fill it in. And you basically do exactly the same thing with images and remote sensing images, right? Okay, I'll skip that. So basically, you take an image, you basically start masking out, and you ask the model to fill in, right? And this builds an intrinsic understanding in the model of what is in these images, basically, right? You do need a lot of data, but image data, right? There's no labels at this point. And like a typical architecture that you will see of these models, this is basically very similar to large language models, is you basically have, you take all of the images across, right? You work on this patch basis, and the encoder essentially produces this low-dimensional representation, right? So you basically go through a bottleneck, and then you blow it up again, right? And you reconstruct the images, and that is your objective, right? Your objective is to minimize the reconstruction error. You can add a few other things as well to make sure, for example, you have temporal consistency, etc. Okay, I think I'm out of time, but hopefully you got an idea, because once you've built this foundation model, then you can just use it directly on basically the set of labels that we have. So for example, we're talking about forest or non-forest, and then very quickly have a model that basically is able to do this classification. Okay, please have a look at the slides. The one point that this is saying, this type of approach is already working on images. So there's a Flamingo model here. So we are already seeing very positive results in remote sensing. And I will stop with this slide. But essentially, why remote sensing is so interesting and so exciting is, although I showed you a lot of optical imagery, there's actually a lot of different types of imagery, right? So we have radar, we have LiDAR, we have all kinds of things. And it's really an ideal domain for an AI approach, right? It's also the temporal aspect is hugely important and valuable because it allows you to understand what's changing. And we can also leverage things with outside imagery with imagery, things like text understanding or seismographer data or magnetic data that the next speaker will talk about. So it's a very kind of exciting space to work in. And I'll stop at that. Yeah, thank you very much.